In the realm of electronic design automation, EDA, technology mapping poses a significant challenge due to the vast number of cells contained in modern technology libraries. This leads to an increasingly large search space and potential overhead. To address this challenge, the authors propose MapTune, a novel framework that leverages reinforcement learning to refine the cell selection process during technology mapping. MapTune utilizes reinforcement learning to make design-specific choices during cell selection, learning from the environment to refine the cell selection process. This approach reduces the search space and potentially improves mapping quality. The effectiveness of MapTune is evaluated on a wide range of benchmarks, different technology libraries, and technology mappers. Experimental results demonstrate that MapTune achieves higher mapping accuracy and reduces delay, area across diverse circuit designs, technology libraries, and mappers. The paper also discusses the Pareto-Optimal exploration and confirms the perpetual delay area trade-off. The post-technology mapping and post-sizing quality of results, (COR), have been significantly improved, with an average area delay product (ADP) improvement of 22.54% among all different exploration settings in MapTune. The improvements are consistently maintained for 4 different technologies: 7 nanometers, 45 nanometers, 130 nanometers, and 180 nanometers, and 2 different mappers. The authors motivate their work by highlighting the limitations of existing EDA tool flows, including the lack of guarantee, large design space, and time-consuming evaluation of design points. They discuss recent advancements in employing decision intelligence in EDA, such as machine learning techniques for automatically configuring tool configurations and exploring synthesis transformations. The technology mapping process faces an increasingly large search space due to the vast number of cells contained in modern technology libraries. The authors argue that carefully calibrated partial technology libraries with a subset of cells can mitigate the search space and reduce runtime. However, the selection of an optimal subset of cells requires significant expertise and experience, which is known as cell selection and represents a significant challenge for EDA. Overall, MapTune addresses this challenge by utilizing reinforcement learning to make design-specific choices during cell selection, resulting in a reduced search space and potentially improved mapping quality. The authors introduce a novel reinforcement learning guided sampling framework, MapTune, to explore the design space of partially selected technology libraries for optimizing technology mapping performance. This work contributes significantly by providing a comprehensive case study utilizing the 7 nanometers ASAP library to showcase the performance implications of various partially random sampled libraries, and introducing a novel cell selection framework based on multi-armed bandit and Q-learning. In the logic synthesis process, technology mapping plays a crucial role in selecting appropriate cells from an EDA library to realize a circuit in a chosen technology. Various algorithms have been developed to address the technology mapping problem, including tree-based approaches, directed acyclic graph-based methods, genetic algorithms, and ML approaches. Technology libraries are also essential in technology mapping, as optimizing or generating standard cell libraries can improve power, performance, and area, PPA, in the design flow. However, there has been no effort to analyze the impact of these libraries on the technology mapping procedure. The authors propose a counterintuitive finding that a partially selected set of cells from the full technology library might significantly improve the technology mapping PPA results. This is attributed to the complexity and algorithmic space of technology mapping algorithms increasing as the number of cells in the libraries increase, while most practical technology mappers are heavily heuristic-based. A comprehensive case study was conducted to explore the impact of specific cell selection within a full library on the technology mapping PPA results using the ABC framework. The MapTune framework was evaluated using designs from 5 distinct benchmark suites and 4 different libraries, demonstrating average area delay product (ADP) improvements of 22.54% by solely tuning the libraries. The authors introduce MapTune, a novel framework that leverages reinforcement learning to optimize technology mapping via library tuning. In their case study, they explore the impact of partial library sampling on quality of results, (COR), in technology mapping. This investigation involves randomly sampling the technology library space using 3 different ranges: 75,100 cells, 100,125 cells, and 125,150 cells. The results, as presented in Figure 1, demonstrate that the sampled partial libraries significantly influence CoR in the post-sizing stage. Larger sampling sizes tend to produce more clustered results, while smaller sampling sizes reveal greater potential for optimization. 3 key observations emerge. First, the sampled partial libraries have a significant impact on CoR. Second, CoR distributions vary significantly with different sampling sizes. And third, technology mapping on partially sampled libraries likely outperforms the baseline, but not for all designs. These observations underscore the importance of tuning the technology mapping library to meet design-specific requirements. The authors then formulate the MapTune framework, which is dedicated to addressing the cell selection problem with a pool of candidates. The framework utilizes the area delay product, ADP, as a single metric to assess overall circuit efficiency. In each decision iteration, a subset of candidates is selected from the library, forming a potential solution. This solution is represented by a multi-hot encoded vector S, where each distinct S represents a unique combination of candidates, each associated with a specific reward. The essential model formulation configurations include the action space, state, and reward. The action space consists of a discrete and finite set of actions, where each action corresponds to selecting a specific cell to form a subset of cells from the technology library. The state S represents the current data collection condition, and the reward function corresponds to the cell selections made by the agent, defined as the negative of the ADP under the current state S. The paper introduces a novel framework, MapTune, which harnesses reinforcement learning to enhance the efficiency of technology mapping in digital circuit design. This framework is designed to optimize the trade-off between delay and area in the mapping process. The authors propose 2 distinct directions for the MapTune framework: multi-armed bandit, MapTune MAB, and Q-learning, MapTune Q. In the MapTune MAB approach, the authors implement 2 algorithms, MapTune Epsilon and MapTune UCB. The MapTune Epsilon agent uses an epsilon-greedy strategy to balance exploration and exploitation, while the MapTune UCB agent integrates a confidence interval around the reward estimates to effectively tackle the exploration-exploitation problem. The MapTune Q approach, on the other hand, utilizes Deep Q Network, DQN, and Double Deep Q Network, DDQN, to approximate the optimal state action value function. The probability of selecting an action is derived from the predicted Q value of the taken action, and the target Q value is calculated using the Bellman equation. The authors also provide a detailed explanation of the probability vector update mechanism for both MapTune MAB and MapTune Q agents. This involves adjusting the probability of taking an action based on the observed rewards and the number of times each action has been taken during previous iterations. The paper presents experimental results from technology mapping of selected designs, showcasing the efficacy of the proposed framework in optimizing delay and area metrics. These results are visualized in Figure 1, which illustrates the performance of the MapTune framework compared to a baseline approach that uses all cells in the original library for technology mapping. Overall, the paper presents a novel reinforcement learning-based framework for optimizing technology mapping in digital circuit design. By leveraging the strengths of both MAB and Q-learning paradigms, the MapTune framework offers a promising solution to the challenge of balancing delay and area in technology mapping. The MapTune framework is a reinforcement learning-based approach for technology library tuning, aimed at optimizing the array-delay product, ADP, of digital circuits. It utilizes a deep Q network, DQN, agent that learns to select the optimal technology library based on the current state of the circuit. The DQN agent is trained using a mean squared error, MSE, loss function to predict the Q values, which represent the expected rewards for each action. The agent updates its parameters using backpropagation to maximize the rewards. To mitigate the overestimation bias in the DQN, the authors propose using a double deep Q network, DDQN, agent, incorporating an additional target network that mirrors the online network. The target network is updated periodically, and the Q-values are calculated using both the online and target networks. The authors evaluate the MapTune framework on 5 benchmark suites, including ISCAS 85, ISCAS 89, ITC, ISCAS 99, VTR 8.0, and EPFL benchmarks. The experiments are conducted using different technology libraries, such as ASAP7, NAN45, SKY130, and GF180. The results show that MapTune is able to converge to a lower achievable ADP within a given optimization timespan. The authors pose 3 research questions to evaluate the effectiveness of MapTune. RQ1: how effective is MapTune in optimizing ADP? RQ2: are MapTune adaptive to different technologies? And RQ3: how sensitive is MapTune to the sampling size? The results indicate that MapTune is able to converge rapidly to a lower achievable ADP, and is effective regardless of the technology library used. Additionally, the results demonstrate that MapTune MAB methods show a slight superiority over MapTune Q methods in terms of general convergence rates and lowest achievable ADP. The authors also provide experimental results for 9 representative designs mapped on the ASAP7 library with a delay-driven mapper. These results show that various MapTune methods are able to converge to a lower achievable ADP within the given optimization timespan. Furthermore, the results demonstrate that MapTune is able to adapt to different technology libraries, and is effective regardless of the sampling size used. A comprehensive comparison of the ADP convergence rates for 9 selected designs mapped on the ASAP7 library, tuned by various MapTune MAB and MapTune Q methods with the ABC delay-driven mapper, reveals that MapTune achieves at least a 4% ADP reduction compared to the baseline. Notably, an average of 36% ADP reduction is observed for design S838A mapped on various technology libraries tuned by MapTune. The effectiveness of MapTune is further evaluated using different technology mappers, including the ABC built-in delay-driven and array-driven mappers. For 8 selected designs with both mappers on different technology libraries tuned by MapTune, the final converged ADP are all brought to a lower level compared to the baseline. For instance, for design S35932, MapTune achieves an average of 40.12% ADP reduction with the delay-driven mapper and an average of 40.00% ADP reduction with the array-driven mapper, demonstrating the algorithm's effectiveness regardless of technology mappers. The Pareto-Optimal exploration capabilities of MapTune are also explored, focusing on the trade-off between delay and area, 2 primary metrics that dictate the efficiency and compactness of a given solution. The results from the delay-driven and array-driven mappers are presented in Table 2 and Table 3, respectively, showcasing the final mapping results for each method obtained at the 1-hour timeout. These findings confirm the perpetual trade-off between delay and area and demonstrate how the algorithm has managed to identify a new frontier that is superior to the baseline. A comparative analysis of the final converged average delay penalty, ADP, for 8 selected designs mapped on various technology libraries, including ASAP7, NAN45, SKY130, and GF180, reveals significant insights into the trade-offs between area and delay optimization. This study compares 2 tuning methods MapTune MAB and MapTune Q with ABC delay-driven, D, and array-driven, A, mappers. The results indicate that MapTune emphasizes delay optimization, resulting in an average delay reduction of 21.77% for delay-driven mappers and 22.30% for array-driven mappers, with modest area trade-offs. Notably, the multiplier mapped with SKY130 library tuned by MapTune MAB achieves a 39.96% delay improvement with a 4.03% area penalty, highlighting the potential of partially sampled technology libraries to introduce new performance Pareto-Optimal trade-offs. However, area optimization can also introduce delay penalties, as seen in the design SQRT mapped on GF180 library tuned by MapTune MAB, resulting in a 1.25% delay penalty but a 14.90% area reduction. These findings underscore the importance of considering both area and delay in the optimization process, as well as the impact of technology library selection on these trade-offs. MapTune, a novel sampling framework, harnesses reinforcement learning techniques, specifically multi-armed bandit, MAB, and Q-learning to optimize technology library tuning within the ABC framework. This approach focuses exclusively on library optimization, resulting in an average area delay product (ADP) improvement of 22.54% and the identification of Pareto-Optimal results. The efficacy of MapTune is validated through extensive evaluations using 5 distinct benchmark suites. A comprehensive review of related work in the field of technology mapping is also provided, including in-time, machine learning techniques for taming the complexity of modern hardware design, end-to-end industrial study of retiming, lambda, learning-assisted multi-stage auto-tuning for FPGA design closure, and others. These studies demonstrate the growing importance of leveraging machine learning algorithms to enhance the efficiency and effectiveness of technology mapping processes. The paper delves into the complexities of technology mapping, highlighting the challenges posed by the increasing complexity of modern hardware designs. It emphasizes the need for innovative solutions that can effectively navigate this complexity and provide optimal results. By leveraging reinforcement learning techniques, MapTune offers a promising approach to address these challenges and improve the performance of technology libraries. The authors discuss the theoretical foundations of their approach, detailing how MAB and Q-learning algorithms are applied to guide the sampling process. They also present a detailed analysis of the experimental setup and results, showcasing the significant improvements achieved by MapTune compared to traditional methods. In conclusion, the paper presents a groundbreaking approach to technology library tuning, leveraging reinforcement learning to achieve substantial improvements in ADP. The comprehensive review of related work underscores the significance of this research, positioning MapTune as a pivotal contribution to the field of technology mapping. Electronic design automation, EDA, has witnessed significant advancements with the integration of machine learning techniques, enhancing efficiency, accuracy, and speed. This convergence has led to the development of novel algorithms and methodologies. Various approaches have been explored, including reinforcement learning, deep learning, and generative adversarial networks, GANs, which have been applied to different aspects of EDA, such as placement, routing, and logic optimization. These advanced algorithms, borrowed from computer science and artificial intelligence, have proven more effective in solving complex EDA problems than traditional methods. The authors also highlight the significance of multi-armed bandit problems and upper confidence bound-based decision-making strategies in dynamic spectrum access, which can be applied to EDA for optimizing resource allocation and minimizing errors. These strategies enable efficient exploration-exploitation trade-offs, allowing for adaptability in dynamic environments. The research has demonstrated the potential of machine learning in EDA, showcasing improvements in design quality, reduced computational time, and enhanced scalability. The integration of machine learning techniques has opened up new avenues for tackling complex EDA problems, enabling the development of more efficient and effective design flows.